Trigonometry. This is a very useful part of mathematics, and you'll find out more as you go along. But we're just covering the basics for now. You do need to know something about x and y coordinates, angle measurements, and particularly Pythagoras Theorem. If you need to study up on those things, do that first, then come back to the video. Okay, let's get started. We're going to move point P, whose x and y coordinates are always the same as one another. We move it away from the origin, and we're going to stop at a special point where the distance OP is exactly 1 unit. Let's look at the triangle underneath point P. Its height is the same as the y coordinate of P, and its base is the same as the x coordinate of P. And both of those are the same size, so it's an isosceles triangle. It's also right-angled, so its angles are going to be 45, 90, and 45, not marked, but 45 on the top. We're now going to take the angle at the origin and increase it. We keep P 1 unit distance from the origin, but notice how the coordinates of the point P change as the angle changes. Sometimes the coordinates are positive, sometimes they're negative. So we've seen how the coordinates change as that angle changes. And we've done a full 360 back to our starting position. Can we work out the actual coordinates of point P? Pythagoras' theorem is all about the squares drawn on the sides of a right triangle. It says that the area of the two smaller squares added together is the same as the area of the largest square. So what's the area of the largest square? Well, its side is 1 unit. So its area is 1 multiplied by 1, which is 1 square unit. This area is the same as the area of the two smaller squares added together. And the two smaller squares are the same as one another. We can check this by splitting each of the squares into equal-sized triangles. Now, if each of these small squares has an area of half a square unit, that means their side lengths must be the square root of 1/2. It also means that the x and y coordinates of point P are each the square root of 1/2. And now at last for some words we use in trigonometry. The height of point P, its y coordinate, is equal to the sine of 45 degrees. And the x coordinate of P is equal to the cosine of 45 degrees. Now we're going to change the angle from 45 degrees to something else. We're going to mark the angle with the Greek letter theta or theta, because that's traditional for marking an angle which is variable. Whatever the angle theta is, the y-coordinate or height of point P is known as the sine of theta, and the x-coordinate of point P is known as the cosine of theta. Watch what happens as we go on increasing the angle of theta. The sine of theta is always the y-coordinate of point P, and the cosine is the x-coordinate of point P. Okay, back to specific angles. We've looked at 45 degrees. What about 60 degrees? I've drawn a circle here with a radius of 1 unit, centre on the origin, just to make things a little clearer. Can you see the equilateral triangle here? I guess you've seen a diagram like this before. and you know that the vertical line through P cuts an equilateral triangle in half. That means that the base of the marked right triangle must be a half. Using Pythagoras' theorem again, we look at the small square. Its side length is a half unit, so what's its area? It's a half times a half. A half of a half is a quarter. The area of the smallest square is a quarter of a square unit, and that's a quarter of the area of the large square. And as the area of the two smaller squares add up to the area of the larger square, the next smallest square must be an area of 3/4 of a square unit. Notice that at the top left I've recorded the sine and the cosine of 60 degrees. Those are the side lengths of the 3/4 square unit and the quarter square unit. Right, let's go back to our 45-degree diagram and let's see if we can use the results we got to find sines and cosines of other angles. We can think of the unit line as having been rotated 45 degrees from the x-axis. We can rotate the line an extra 90 degrees, ending up at 135 degrees. The sine of 135 degrees will be equal to the y-coordinate of P, and the cosine of 135 degrees will equal the x-coordinate of P. Both the sine and the cosine of 135 degrees are equal to the square root of a half, except that the cosine is negative. Let's rotate another 90 degrees. Notice that the sine and the cosine are now both negative. Rotating another 90 degrees, the sine stays negative, but the cosine has become positive once again. Here's a summary of those results. You can pause the video if you want to study it a little bit further. Right, to finish up, let's take our 60, 90, 30 triangle on a quick spin around the origin. Remember that the sine of 60 degrees is the square root of 3/4 and the cosine is the square root of 1/4. Here is the sine and the cosine at 120 degrees. We'll go quite quickly through some other angles now, building up table of results. Just pause if you want to take your time at any point in order to study what's going on. Lastly, here are all our results in one diagram. Use the pause button if you want to take your time to study it.